In this video, we'll talk about the idea of linear independence of vectors, which ends up being really important when we go back to talking about differential equations that will involve these vectors. So spanning sets for a given vector space or subspace are not unique. There are many different spanning sets for our normal two-component real number vectors, like this list here. And you can check that for all of these, it is possible to solve for constants to hit any real number you want. As an example, right, you could set up the augmented matrix for 1, 0, 0, 1 for this first one here, equaling a, b for any vector a, b. So c1 is 1, c2 is b, and you're done. The other ones require more work. For instance, something like 1, 2, 3, 1, a, b. We'll need some row reduction, but it will work to get you to the answer. And it'll work for all of these. But what's different here? Well, these first three all have two vectors in them. The last, though, has three. So the matrix is a little bit different, just because it's bigger. But you can still solve this. But is there an important difference between the two vector spanning sets and the three vector spanning set? It turns out there is, and that's the idea of linear independence. Which really comes down to, is there a reason why I need three vectors in that last set, or could I get away with two? That's where this idea comes into play. So solutions to differential equations have been talked about as being linearly independent before. It means that they're different enough to meet initial conditions. That ends up being the same root definition we're using here for vectors, but it looks a little different at the outset because we're talking about vectors, not solutions first. So we say that vectors v1 through vn are linearly independent if the only way to satisfy c1 v1 plus c2 v2 plus all the way up to cn vn equals 0 is by setting all of the c's equal to 0. Right? Clearly doing that works. If all the c's are 0, then I get 0. Great. But I want to make sure that's the only way to satisfy this situation here. If not, we say the vectors are linearly dependent. And by if not here, I mean if there is some other solution to make this equation equal to 0 without making all the c's. So some examples of that are the vectors 1, -1, and 0, 1 linearly independent. What about this other set? So let's start with that first one. I want to find c1 and c2 to make 1 - 1 c1 plus c2 0 1 equal to the vector 0 0. This just tells me that c1 plus 0 c2 equals 0, and the negative c1 plus c2 equals 0. The first forces c1 to be 0, then the second then forces c2 to be 0. So the only solution here is 0 0. So these are linearly independent. What about the other set? Well, for the other set, I want to find c1, c2, and c3 so that c1 times 1 1 plus c2 times 3 2 plus c3 times 2 1 equals 0 as a vector. Now you could do this by some sort of row reduction procedure, put it in the matrix and go. From here we can kind of see that right off the bat, 1 1 plus 2 1 equals the vector 3 2, which is the last vector in our set. Which means if I pick c1 to be 1, c3 to be 1, and c2 to be -1, I get that 1 times 1 1 minus 1 times 3 2 plus 1 times 2 1 equals the 0 vector. And so these are linearly dependent because I found a solution that did not involve setting everything equal to 0. Now, if there are more than one solution, I could also do 2 - 2 and 2. That would also work. Any sort of multiple of this equation would give me another solution to this problem. What we can see from this process here is that determining linear independence really comes down to solving a system of equations for these constants c1, c2 up to cn that make this thing being 0. And in particular, since the right-hand side is 0, it's a homogeneous system of equations. This means we can jump back to our matrices and row reduction, like I vaguely mentioned before, to work this out. So we want to find c1 through cn so that c1 v1 plus c2 v2 up through cn vn equals 0. But I can rewrite this equation here as a matrix A times a vector C equaling 0, where A is the matrix with columns v1, v2, up to vn, and C is the vector containing these C constants. That's the same thing written in matrix vector form, which means we're looking for the kernel of this matrix A. How can we characterize this? By looking at the reduced row echelon form or the row echelon form of the matrix A. You can row reduce A and look at the pivot columns. If we have any non-pivot columns, that means that we have a non-zero solution to this homogeneous equation, which means the vectors are linearly dependent. And in particular, a non-pivot column tells me I can write that vector, the vector that came from that column, as a linear combination of the vectors that are in pivot columns. Because it comes from the fact that this could be a free variable in my solution. Whenever I pick for this, I can find values for the other ones to make it work out. Another option here, you could also write the vectors as rows and row reduce. Now this doesn't come directly from the idea of the equation we're trying to solve, but the operations in row reduction are linear combinations. In particular, they're linear combinations of the rows, which means that I can do this to simplify what this looks like. This gives me a simpler way to characterize the span of these vectors, in addition to knowing if they're dependent or independent. For the example of using the first of these techniques, I want to find a linearly independent subset of these vectors here. So I have these vectors, and I want to say, how many of them do I need to get a linearly independent subset? Right? This thing may be dependent or independent, but if it's linearly dependent, I can take vectors away until it becomes linearly independent. And I want to figure out how many I have to take away and what can I use for these independent vectors. We're going to take this, put them into a matrix of columns, and do row reduction. If you want to do it on your own, pause right now and then go ahead and work through it. Otherwise, I'm going to go skip through the whole steps and get to the end of the row reduction here. And that gets us here. So I shortcut this a little bit because I recognized at this part here that I had two identical rows and that this row was -2 times the other one. So I could, at this point, cancel things out before I divide through by 19. And if you wanted to divide by 19 to get this to actual row echelon form, you could. You have a 1, a 15 over 19, and a 4 over 19 here. But what I need for this setup here is I need the pivot columns. So I get that column 1, column 2, and column 3 are pivot columns. That'll be a 1 when I divide by 19. And so that means that these vectors are linearly dependent. And I can take the first 3 to use as my linearly independent subset. So I can take the first 3 vectors as a linearly independent subset of this set of vectors. This is not unique. If you had reordered your matrix from the start and put the columns in a different order, you'd have gotten a different independent subset. And so this is not unique here, and we'll see the unique part of this with our next topic that we'll get to. This is the idea of linear independence. This idea of vectors sort of being independent means I can't write one as linear combination to the other ones, and sort of has something to add to the span of these vectors. Right? If it's a linear combination, it doesn't add to the span at all because it's already sort of there. In this case, linear independent vectors add to the span. So that's important to think about these things when we start trying to talk about solutions to equations and when things are useful to have in a solution. Because if they're not independent, there's no real point in having them there.